Hi, in this video I'll show you how to use a parallelogram to choose the right trigonometry for pretty much any forces problem. And by the way, do give it a look, even if you've tried using parallelograms before and decided you didn't like them at all. And this often happens. You might have decided that you prefer to stick with one triangle instead of two. And a single triangle can often be fine, and it is after all how you probably learnt to add and subtract vectors, as though the vectors are journeys, and then what we take to be the sum total of any two of them is just like going, as we say, as the crow flies, which is to say, a straight journey beginning and ending the same. And that's fine if it works for you, and if you never have any trouble deciding how to arrange the triangle. But with forces, that way the single triangle is missing a trick, which is that with a parallelogram you can always imagine the vector arrows as strings literally pulling, and in fact you draw them all as coming out from the same point, the same particle that they're pulling. And then it's totally natural and intuitive to see the middle string as having the same effect as the other two acting together. Imagine this one pulling at the same time this one is pulling. You know the particle will move roughly in this direction, somewhere in between. And then you can feel that the trigonometry is just going to make this more precise. Now you might have noticed a bit of cheek here. For a start, plenty of forces push, not pull. So that's a bit of poetic license. But also for the trigonometry to work as we feel it should, we must be pretending that the lengths of the strings depend somehow on how strongly they are pulling. Otherwise, how is trigonometry going to tell us the resulting direction of movement? And we don't normally make any such assumption. But yes, this is exactly what you do want to pretend. That you can see the strength of a pulling force in the length of the string pulling. And you'll find it's totally reliable, and you can feel sure that you've chosen the right trigonometry this way. Always sketch. It doesn't have to be a great sketch, something freehand or with a set square. Also go here to this drawing machine if it might help you at all for teaching or learning. And do let me know if it does, or if you have any questions or problems. Thanks. And now an example. Okay, question 6. Two particles P and Q joined by a light inextensible string, which we can therefore assume has a constant tension, and we're asked the tension at the initial stage when P is held at rest by unspecified thumb and forefinger. And we can do this by looking at Q and seeing that only two forces are experienced by Q. Q experiences its weight pulling down and the tension of the string pulling it back up, and these balance. So when they say state the tension, that seems to imply that there isn't much work to do, and so it is. T just is equal to 0.2 G because those two forces balance in equilibrium. After the thumb and forefinger go away though, what's going to happen to P? Well, we can see whether it's going to move up or down the slope by comparing with the situation of a smooth plane. This is a rough plane, but even so, while P is still held in place, suppose the plane were smooth. P would still be subject to a force of this magnitude, the tension in the string, and that tension would be acting up the slope, parallel to the slope. But the weight of P is going to be the same as the weight of Q because they both have the same mass, 0.2. So vertically, the weight acting on P is going to be the same as the weight acting on Q. But of course that weight is not allowed to act on P unhindered. It's hindered by the plane, which has a reaction force perpendicular to the plane, and that's going to take some of the weight away. So that acting down the plane, we can see that, okay, 0.2 g here vertically, but acting down the plane a good deal less. And of course, also, we can see the trigonometry involved here is going to be quite simple. Theta here, this angle here, is clearly 30 degrees. So in fact, the amount of P's weight acting parallel to the slope is going to be precisely half of 0.2 g only. So if the plane were smooth, tension would win out over weight, and P would be moving up the slope. The plane isn't smooth, but the friction isn't going to help P either way. And if P can't even move down the slope with no friction, it certainly can't move down the slope with friction. So if P is moving at all, it must be moving up the slope. So let's assume then that P is moving up the slope and Q is moving vertically down. Now Q is still only experiencing two forces, but tension, we think, is probably going to be rather less than the weight of Q. If tension were more, then Q would be moving up, clearly. But tension is probably somewhat less. So what we can do here is start to form an equation of motion for Q. We can say that, a bit like back with these momentum diagrams, we can do subtraction here. We can say the force with which Q is actually moving downwards, well, if it weren't for the tension, MA for Q would be precisely 0.2 g. But with tension holding it back, however much, MA for Q, 0.2A, is going to be the weight of 0.2 g, or 1.96, minus whatever t is. So we've got an equation of motion, which is going to be one of two. So now let's form a similar equation of motion for particle P. After P is released from rest, what are the forces acting on P? Well, quite a few. As is typical in these situations, we've got quite a number, and it's worth drawing them as though they all had the same magnitude, just for the sake of thinking what forces are possibly involved here. All of the forces acting on P are the tension up the slope, friction down the slope, weight vertically down, and reaction perpendicular to the slope. So a weight of 1.96, T, which is going to have the same magnitude as T over here for particle Q. Okay, and we'll see where these numbers came from now for R and F. In fact, F, the number we've got there, is precisely 0.4 of that reaction force there, because that's what the coefficient of friction tells us, isn't it? It gives us the friction as a proportion of the normal reaction. So how did we get a normal reaction of 0.98 times root 3? Just by following through on the trigonometry that we alluded to. Parallel with the slope, we've got half of 1.96, 0.98, and cos 30, whereas sine 30 is a half, cos 30 is root 3 over 2, so it's going to be root 3 times as much as this component here. So 1.96 cos 30 was useful for finding the reaction, the magnitude of the reaction force from which we can get the friction. And now we can form our equation of motion for particle P. We can see tension acting up the slope and friction along with weight acting down the slope. And then MA for particle P is going to be what's left of the tension magnitude after we've subtracted these retarding forces of 0.98 and 0.392 root 3. Okay, so up here we've got 0.2a equal to this stuff, and here we could say we've got 0.2a equal to that stuff is our second equation of motion. So 0.2a equals this stuff and also equals that stuff. Therefore, this stuff equals that stuff. And then we just balance to solve for t. And so question 1 has two parts. Before p is released from rest, we saw that it was just this simple situation here. T is 0.2g, and then afterwards t is 1.81. And then the next episode, what happens? Q strikes the floor. Well, in that case, P is not being pulled by the string anymore. In other words, in this second situation, this equation of motion picture for P, after Q has hit the floor, P must disappear. Away it goes. But then let's look at the MA for P now during this episode. It's still 0.2a because the mass is still 0.2. But MA for particle P now is simply going to be a retarding force being the sum total of these two retarding forces. The weight acting down the slope and the friction Yes, the weight acting down the slope and the friction acting down the slope. I wobbled then because we've got MA pointing down the slope, so I thought that the friction should be acting against that and up the slope. No. I'm confused, aren't I? Because the particle P, we mustn't forget, is still moving up the slope. This force is a retarding force, and it is going to be the sum total of these two retarding forces. In other words, the force with which P is slowing down, MA, its rate of change in momentum, is going to be exactly equal to the sum total of these two retarding forces, which is going to be 0.98 plus 0.67896, so 1.65896. So the retarding or decelerating force is 1.65896, and that's a fifth of the acceleration. So we can infer that the acceleration is 5 times that. Here we are, 8.2948. And now we've got the acceleration, we've got a distance, we've got a final velocity of 0. They want the initial velocity for this episode when P is still continuing up the slope. We'll use a suvat because, rather than a graph would be overkill because T isn't involved. So this particular suvat is usually worth using straight off. So final velocity of 0. And then we can solve for u squared, the square of the initial velocity, because we had 0 equals u squared minus double this acceleration of 8.2948 times the distance. And so we get, finally, the initial velocity. Part 3, calculate the magnitude of the contact force exerted on P while P is in motion. In motion which way? Up or down the slope? We haven't got to the down the slope episode yet. For both of the episodes we have looked at, we've got friction acting down the slope, and anyway, even if friction were acting up the slope, the problem would still be the same. We'd still be doing Pythagoras on the two components of the contact force, which are, and that's the trick to this really, just knowing that the contact force usually be analysed as a combination of friction and normal reaction. and because they're perpendicular we just do Pythagoras on those. So we're going to have the square root of the square of this, which is going to be 3 times the square of 0.98, plus the square of this, which is going to be 3 times the square of 0.392. So we can take the 3 out of it really, and we can just say it's going to be root 3 times that bit of Pythagoras. And that's question 6. Question 7.